Reductive elimination reaction. Dear students, I am Dr. Digna. Reductive elimination reaction. We know reductive elimination is the reverse of oxidative addition reaction. In this case, Ml4 reacts with XY, giving oxidative addition reaction to give L4M XY. That is, the coordination number of reactant increases by 2 units and the oxidation number also increased by 2 units. That is oxidative addition reaction. Just reverse of this reaction is known as reductive elimination reaction. That is when L4MXY giving Ml4 plus XY. By this reaction, the coordination number here is 6 and the oxidation state is Mn plus 2. That is reduced by reductive elimination reaction by 2 units to Mn plus and coordination number decreased by 2 units to 4. This reaction is actually known as reductive elimination reaction. The opposite of oxidative addition, where two ligands couple and eliminate from a metal center, is known as reductive elimination. Reductive elimination is an elementary step in organometallic chemistry in which the oxidation state of the metal center decreases while forming a new covalent bond between two ligands. Here, a platinum complex, platinum is in the 4 oxidation state and it is an 18 electron species. After reductive elimination by a methane molecule from this, and it is converted into 16 electron species and its coordination number decreased by 2 units and its oxidation number decreased by 2 units. So it is an reductive elimination reaction. So it is an important step in organometallic chemistry. Oxidative addition and reductive elimination reactions are in principle reversible reactions. The same mechanisms can apply for both the process, and the product equilibrium depends on the thermodynamics of both directions. However, in practice, one direction is normally or thermodynamically favored over the other. Oxidative addition happens. It is actually the reverse of reductive elimination reaction, but it is in some cases it is one direction is normally thermodynamically favorable over the other reaction. Oxidative addition and reductive elimination reactions play a major role in catalytic processes. Reductive elimination is often the product forming step in many catalytic processes. We have already studied in Monsanto acetic acid process and other catalytic conversions in using Wilkinson catalyst, that is in hydrogenation reaction and hydroformylation reaction. In all those processes involving or the catalytic loop involving the reductive elimination reaction to produce the product. Reductive elimination is often seen in higher oxidation states and can involve a 2 electron change at a single metal center or a 1 electron change at each of 2 metal centers, that is binuclear or bimetallic. Here example, a compound, here the coordination number is higher than the product by 2 units and the metal is in the higher oxidation state than the product. So it is an reductive elimination reaction. If it is a bimetallic one, 2 metal centers involved, there is only a 1 electron change. If it is a single metal center, there is a 2 electron change occurs. For a mononuclear reductive elimination, the oxidation state of the metal decreases by 2 while the d electron count of the metal increases by 2. This pathway is common for D8 metals, that is nickel 2, palladium 2 and gold 3, and D6 metals like platinum 4, palladium 4, iridium 3 and rhodium 3. Additionally, mononuclear reductive elimination requires that the groups being eliminated must be cis to one another on the metal center. The reductive elimination happens only when the eliminating groups are cis to one another on the metal center. For example, here the palladium and the reductive elimination occurs to ethane molecule at 80 degrees Celsius in dimethyl sulfoxide. It forms to ethane and palladium metal. This is a reductive elimination reaction. And in the case of a presence of a bulkier metal, ligand here, this reaction at the same reaction conditions and with the same solvent, there is no reaction occurs, because here it is not in a cis position, so there is no reductive elimination occurs. For binuclear reductive elimination, the oxidation state of each metal decreases by 1, while the d electron count of each metal increases by 1. This type of reactivity is generally seen with the first row metals, but also seen in both second and third row metals. First row metals which prefer a 1 unit change in oxidation state. And reductive elimination reactions require both eliminating fragments to be cis to each other and are best thought of as the reverse of the concerted form of oxidative addition reaction. For example, here a binuclear complex or a metal carbonyl, that is here 2 osmium metal atoms, so it is binuclear, and it is the eliminating group is methane, CH3 and hydrogen is in the cis position. It is applied thermally or photochemically. The energy is applied thermally or photochemically to this system. Reductive elimination happens by the elimination of methane from this, and here the osmium metal, the oxidation state decreased by 1 unit for each osmium metal. A reaction sequence that appears to be an oxidative addition followed by a reductive elimination may in fact be the exchange of two species by a process known as sigma bond metathesis. This is a special type of reaction which involves a sequence of reactions like oxidative addition followed by reductive elimination and exchange of two species. Bond metathesis reactions are common for early D metal complexes. So, where there are not enough electrons on the metal atom for it to participate in oxidative addition reaction. For example, the 16 electron compound zirconium complex, that here ligands as attached to the zirconium metal is 2 cyclopentadienyl rings and 1 hydride and 1 methyl group. To this, hydrogen is added, but this compound cannot react directly with hydrogen to give a trihydride ion or trihydride complex, because all its electrons are involved in bonding to the existing ligands. Zirconium metal is bonded to, or ligands are bonded to this zirconium metal. These electrons are involving in bonding to with the existing 4 ligands. So there is no additional electrons to participate with the hydride formation, trihydride formation with the hydrogen molecule. So there will be a 4-member transition state is proposed for such a reaction, such a bond metathesis reaction occur. Here first bond making occurs with this hydrogen molecule and then bond breaking, and here the bond breaking occurs to give zirconium hydride, which is already there, and in the place of methyl there is another hydrogen atom is attached, and with this methane is formed by the elimination of methane by reductive elimination reaction. So it is a special type of sigma bond metathesis reaction, that is oxidative addition followed by or in a followed by a reductive elimination reaction in a sequence, a reaction in a sequence, or a sequence reaction involved. Both oxidative addition and reductive elimination occurs. Suggest a likely reaction pathway, that is the sigma bond metathesis, for the following transformation. The reaction with the hydrogen dihydrogen cannot proceed through the dihydrogen complex by oxidative addition to a dihydride and then reductive elimination of butane takes place in a sequence or in a series of reactions like oxidative addition and reductive elimination, because the lanthanoid compound is incapable of oxidative addition reactions directly. So there is a possible scenario involves a bond metathesis reaction through an intermediate such as a 4-centered transition state. Here the bond formation and bond making and bond breaking occurs, and by this here the bond formation occurs and here the bond breaking occurs, and butane is eliminated from this compound and a hydride complex is formed. Mechanism for reductive elimination reaction. Several mechanisms are possible with reductive elimination reactions. The prominent mechanism is a concerted pathway, meaning that it is a non-polar 3-centered transition state with retention of stereochemistry. SN2 mechanism, which proceeds with inversion of stereochemistry, or a radical mechanism. The rate of reductive elimination is greatly influenced by the geometry of the metal complex. That we know in the case of oxidative addition reaction, there is, if non-polar compound, the mechanism is a concerted pathway. In a SN2 mechanism, if it is a polar compound, that is proceed with the inversion of stereochemistry or with a radical mechanism. The rate of reductive elimination is greatly influenced by the geometry of the metal complex. For example, in the case of octahedral complexes, the reductive elimination can be very slow from the coordinatively saturated center, and often the reductive elimination only proceeds via a dissociative mechanism, where a ligand must initially dissociate to make a 5-coordinate complex. The 5-coordinate complex that is eliminated from one ligand from the octahedral complex, here it is shown as an example of rhodium complex. Here the trimethyl phosphine is eliminated and adopts a trigonal bipyramidal structure, and here it is a 5-coordinate complex, adopts a Y distorted trigonal bipyramidal structure, and it is converted into a Y type distorted trigonal bipyramidal structure. And after elimination of a T-shaped 3-coordinate complex is formed which will associate with a ligand to form a square planar 4 coordinate complex. Here the elimination is like that. CHM is CO, CH3 is acetone is eliminated from this, and here a T-shaped molecule is formed, 3 coordinate complex is formed. To this another trimethyl phosphine is attached to this, form a square planar 4 coordinate complex. That means here reductive elimination occurs from this octahedral complex to a square planar complex. Here coordination number is 4 and here it is coordination number is 6. I will explain once again. That is, in the case of octahedral complexes, elimination of one ligand to form a 5 coordinate complex, that will the 5 coordinate complex adopts a Y-shaped structure. That is, here it is in the form of a Y-shaped structure. Y-shaped structure, and it is associated, and this hydrogen and acetyl group is removing the acetone from this compound and forming a T-shaped compound. This associated with another trimethyl phosphine to form a square planar 4 coordinate complex. This can be seen in the elimination of 2 ligands from an octahedral metal ligand complex, reducing the metal to a lower oxidation state. That is, in general, the reduction of a transition metal in an octahedral complexes reduces the number of electrons around it by 2, from 18 to 16. It is an 18 electron species, it is an 16 electron species after reductive elimination. So this is just opposite of the oxidative addition reaction. In the case of square planar complexes, reductive elimination of square planar complexes can progress through a variety of mechanisms: dissociative, non-dissociative and associative. A dissociative mechanism for square planar complexes initiates with the loss of a ligand. That means always dissociation takes place by the elimination of a ligand. In the case of complexes, generating a 3 coordinate intermediate that undergoes reductive elimination to produce a 1 coordinate metal complex. For a non-dissociative pathway, the reductive elimination occurs from the 4 coordinate system to afford a 2 coordinate complex. If the eliminating ligands are trans to each other, the complex must first undergo a trans to cis isomerization before eliminating. In an associative mechanism, a ligand must initially associate with the 4 coordinate metal complex to generate a 5 coordinate complex that undergoes reductive elimination, synonyms to the dissociation mechanism for octahedral complexes. So square planar complexes can have a variety of mechanisms. First one is dissociative, second one is non-dissociative, and the third one is associative. A dissociative mechanism for a square planar complexes initiates with the loss of one ligand in a dissociative mechanism and forming a 3 coordinate compound, and from this elimination, reductive elimination happens. And in the case of non-dissociative pathway for the reductive elimination in a square planar complexes, here the eliminating group is here is phenyl nitrogen toluene twice. This group is in the trans position first isomerization takes place, and in this case here it is in the cis position. After this, reductive elimination takes place. In an associative mechanism, the ligand must initially associate with the 4-coordinate metal complex to generate a 5-coordinate species. From this, it will undergo reductive elimination. Here, ethane is eliminated. This is an associative mechanism. Factors that affect reductive elimination is: reductive elimination is very sensitive to a variety of factors, including metal identity and electron density, steric factors, participating ligands, coordination number of the metal, geometry of the complex, and photolysis or oxidation. Additionally, because the reductive elimination and oxidative addition are reverse reactions, any steric or electronic effect that enhances the rate of reductive elimination must thermodynamically hinder the rate of oxidative addition reactions. We know these are reverse reactions, but only one favor at a particular time. That is, one must be thermodynamically hindered. If reductive elimination happens, oxidative addition reaction thermodynamically hindered, or vice versa. First row metal complexes tend to undergo reductive elimination faster than the second row metal complexes, which tend to be faster than the third row metal complexes. Actually, which is the rate of reductive elimination reactions. This is due to the bond strength, with metal ligand bonds in first row complexes being weaker than the metal ligand bonds in third row complexes. Additionally, electron poor metal centers undergo reductive elimination faster than the electron rich metal centers, since the resulting metal would gain electron density upon reductive elimination. This is an example of reductive elimination reactions. Reductive elimination generally occurs more rapidly from a more sterically hindered metal center, because the steric encumbrance is elevated upon reductive elimination. Additionally, wide ligand bite angles that we are already seen in the case of substitution reactions generally accelerate reductive elimination, because the steric force eliminating groups closer together, which allows for more orbital overlap. So in the case of here, the rate constants is 2.1 into 10 raised to minus 6, but in this case, this is a bulkier group. The rate of reaction is, that is, the bite angle is 100 degree, and here the rate of reaction is decrease. Reductive elimination occurs more rapidly for complexes of 3 or 5 coordinate metal centers than for 4 or 6 coordinate metal centers. For even coordination number complexes, reductive elimination leads to an intermediate with a strongly metal ligand antibonding orbital. When reductive elimination occurs from the odd coordination number complexes, the resulting intermediate occupies a non-bonding molecular orbital. For example, here the flexible phosphine, here the phosphine ligand is this, it is dissociates easily than the rigid phosphine ligands here. If we are using rigid phosphine ligands, it cannot dissociate. If we are using flexible phosphine ligands like this, it will dissociate. Effect of solvent in reductive elimination reaction. That solvent can influence the reductive elimination reaction. Solvent leads to the formation of different elimination products. If we are using polar solvent, we will get a coordinatively unsaturated intermediate first and then elimination product. Here, from the compound or complex platinum complex. Here we are using a polar solvent, and we will get the product as ethane here. But in the case of we are using a non-polar solvent with the same complex, we are getting, without forming an intermediate or 5-coordinate intermediate, we will get another eliminated reductive elimination product as methyl acetate. Effect of added ligands. Added ligands can inhibit or increase or have no effect on the rate of reductive elimination. It can sometimes inhibit the reaction, and sometimes it increases the rate of reaction, or in sometimes there is no effect on the rate of reductive elimination reactions. So for reductive elimination to occur, there are some factors that we have already discussed. Once again, I will tell you, the eliminating groups must be cis to each other, a high formal oxidation positive charge on the metal, the presence of bulky groups on the metal, an electronically stable organic product. These factors affects the reductive elimination reaction. Applications. Reductive elimination has found widespread application in both in academia and industry. We know hydrogenation reactions, there is the product forming step is reductive elimination step, and in the case of Monsanto acetic acid process, and also in the hydroformylation process, and there is some cross-coupling reactions. These reactions are involved in reductive elimination reactions in industry, and also in many of these catalytic cycles. Reductive elimination is the product forming step and regenerates the catalyst. However, in the Heck reaction and the Walker process, the reductive elimination is involved only in catalyst regeneration, not in the product forming step, because in this case reactions, the products are formed via beta hydride elimination reactions. Thank you for hearing me.